Solids of revolution. The washer method. What is a washer? A washer is a thin, circular metal plate with a hole in the middle, as you can see in the figure below. To find the area of a washer, we subtract the area of the inner circle from the area of the outer circle. What is the washer method? Consider the region below. When this region is revolved about the x-axis, we generate a solid that has washer-shaped cross-sections. That is, the cross-sections are in the shape of circular discs, but they have holes in the middle. We can see from the figure below that the radius of the hole in the middle is g of x. That's our inner radius. And the radius of the larger circle, the outer radius, is f of x. To find the area of our washer-shaped cross-sections, we need to subtract the area of the inner circle from the area of the outer circle. The radius of the outer circle is f of x, while the radius of the inner circle is g of x. So to get the area of the outer circle, we take pi and multiply it by the outer radius squared. That is pi times f of x squared. To get the area of the inner circle, we take pi and multiply it by the inner radius squared. In this case, pi times g of x squared. Since both terms have a factor of pi, we can factor out the pi, which leaves us with the quantity f of x squared minus g of x squared. Therefore, the volume of the solid is given by the antiderivative from a to b of pi times the quantity f of x squared minus g of x squared with respect to x. The application of this formula is called the washer method. Now we're going to look at an example of an application of the washer method. The directions here are to find the volume of the solid that results when the region enclosed by the given curves is revolved about the x-axis. Here we have the curves y equals the square root of x and y equals x. Let's label the information that we're given. The top curve here is y equals the square root of x, and the bottom curve is y equals x. Okay. So before we begin, we first need to figure out where these curves intersect so that we can figure out our bounds of integration. So to begin, we will set y equals x to the function y equals the square root of x. Then to remove the square root, we can square both sides so that we have x squared equals x. Next, we can subtract x from both sides so that we have x squared minus x equals 0. Then we can factor an x on the left-hand side, factor out an x on the left-hand side, which leaves you x minus 1 equals 0. And lastly, if you set each of these factors equal to 0, the solution is x equals 0 and x equals 1. So the lower bound of integration is 0, and the upper bound of integration is 1. To find the volume, once the region is revolved about the x-axis, we need to know the inner radius and we need to know the outer radius. As you can see from the figure, the inner radius is the curve x, and the outer radius is the curve the square root of x. Again, the inner radius is x, and the outer radius is the square root of x. So to find the volume, we will integrate from 0 to 1 pi times the outer radius squared. Our outer radius was the square root of x. We will square it, and then we subtract the inner radius squared. The inner radius is just x. We will square it, and we will integrate with respect to x. To clean this up a little bit, we will take the pi and multiply it on the outside of the integral. So we have pi times the antiderivative from 0 to 1. Once we square the square root of x, you're left with x. And when you square x, you have x squared. So we have pi times the integral from 0 to 1 of x minus x squared with respect to x. At this point, we can go to the graphing utility to find the antiderivative of x minus x squared from 0 to 1. When we get this answer, we will simply multiply it by pi to get the volume. To compute the volume using the graphing calculator, we will click the Math button, and under the Math button we will choose the 9th option, which is FNINT, and we're going to integrate the function x minus x squared. So we put in the function x minus x to the second power, followed by a comma, and then x, which lets the calculator know that we are integrating with respect to the variable x, followed by another comma, and then we input the bounds of integration. The lower bound is 0. We will follow that by a comma, and then enter the upper bound of integration, which is 1. Close your parentheses, and then hit enter. And we have approximately 0.167. To convert this decimal to a fraction, we will use the Math menu again, and then we'll use the first option. This option will convert the decimal to a fraction, and we have 1/6.